The infinite line that we examined earlier and did not have a termination point on the right side, so nothing was connected to it. The incoming wave from the left would propagate endlessly in the positive x direction. But sorry, now this line is no longer infinite length, as it now has a load connected to the right side with an impedance of ZL. When the instant wave propagates in the positive x direction, it must eventually encounter the termination point like a wall. As a result, a portion of the signal is reflected back. So the solution of the line equations contains two components, one describing the wave propagating in the positive x direction, and the other describing the propagation in the negative x direction. The propagation in the negative x direction corresponds to the refracted wave. To facilitate this discussion from the perspective of the terminal load, let's shift the reference plane from the leftmost side to the rightmost side of the terminal interface. This allows us to examine the input impedance and reflection coefficient when a load is connected to a line of a given length L, as viewed from the left side of the line. When we shift the reference plane, the original equations for voltage and current waves are rewritten as follows. The instant wave that was initially propagating in the positive x direction is now propagating in the negative d direction, and the refracted wave is now in the positive d direction. The original coefficients a and b are now expressed in terms of a1 and b1, reminding us that the equations used start from the endpoint of the load. Let's look at the picture on the left. This depicts an infinite line with only the instant wave a times exponential to negative j beta x. We can focus solely on the voltage wave, which has a constant amplitude of a. The right figure illustrates the scenario where the line has a finite length. We observe that at various positions d along the line, two waves are synthesized, one in the negative d direction for the incident wave, and another in the positive d direction for the refracted wave. The new phasor at position d is denoted by V of d, and is the result of synthesizing the incident and refracted phasors. Therefore, at each position, we see a voltage wave that has undergone interference and becomes a combination of the incident and refracted waves. The extreme scenarios are fully constructive interference and fully destructive interference. Let's now consider the infinite length scenario. In the figure, Vm denotes the wave amplitude. As time progresses, there is a time-varying sinusoidal wave at position x1. Now that our focus is shifted to positive x direction, the incident wave at each position x2, x3, and x4 only differs in phase, but the amplitude remains constant. Now let's examine the case of the terminated line, where the incident and refracted waves interfere with each other. At each point along the line, the wave amplitude varies depending on the position, as it results from the combination of two waves. We connect the head and tail of the wave at each position, take the real part, and obtain its time domain waveform. For instance, at position D1, the wave changes with time as shown. As we move to position D2, the amplitude may decrease due to the interference of the reflected wave. At position D3, the amplitude is further reduced due to the interference. And finally, at D4, the amplitude decreases even more. So here is a small conclusion. If we have an infinite lossless line, the wave amplitude stays constant regardless of a position. However, if we have a finite length line, the wave amplitude changes as a result of incident and reflected waves interfering with each other. This resulting wave is called a standing wave, which is synthesized from the incident and reflected waves on the line. The voltage standing wave ratio VSWR is often used to describe this situation. When there is more reflection, there will be a higher VSWR, indicating that the wave amplitude varies more significantly with the position X on the line.